generating arrays and matrices. It might be different from what you have learned during linear algebra, just the Python naming convention and how they approach this, or it might not be different. I found it different given my background, but it might not be the case for you. Anyways, I'm gonna explain them. Arrays and matrices are kind of the key for numerical computation, and they are the core and the heart of it. So it is essential to know how to develop them and how we can develop them. One of the most general one, and not because they're complex, they're not important. Like sometimes they're really important. We use them to make coordinate vectors or the grid lines. We use them to sample data. They are regularly spaced elements. So line space and log space. Log space, I think, physicists use more than engineers. But line space is what we use especially for data sampling a lot. Line space accepts an start and end point, and the number of points we want to be generated between those two. So it's a regular, it is when we know how many elements we want, we know start and end, we use line space. And a log space is just a logarithmic way of spacing them. So it is defaulted on 50. If I say I need a line space, which is an array going to be generated from 1 to 10, it's going to give me 50 number between 1 to 10, including 1 and 10. So line space, I could have asked for 10, and it gives me 10 numbers. And I could have given a minus number, but and it would have generated number. But if it was 10 to minus 10, remember this is a step, I would have received an error. 10 to 10, sorry, it just repeats it. From 10 to minus 10, 25 steps. From minus 10 to 10, and I get the results. I could have even asked for minus 20. Yep, this is what I meant. Must be non-negative. This step must be non-negative. And then we have the line space. I just put them next to each other. As you can see, it starts from e minus 10 to the power of minus 2 and goes to 10 to 10. E10 here you can see with 50 values there, or I could have asked for 10, then it is 10 minus 2, 10 minus 1, and then it just generates what needs to be generated. This is 4.6, and then it is 100, 2000 something. It just starts generating those till it reaches to 10 to the power of 10. So these are important regularly spaced elements. There is an alternative way of doing line space. So if you have noticed, line space, they are coming from NumPy, which is a numerical computation realm. So they are by default an array. But that's what I meant, like with CS-oriented tutorials. Like lists are not arrays, so we have the difficulty using them for computational purposes, but they structure the lists the same, the line space, equally spaced elements. So list and range, they provide a list of numbers that we don't know how many we want. We don't care about the number of points between those two numbers. We just know the step. We care about the step, and the increment size or decrease size is 2 here, like here is increase. So from 2 to 30, go every 2 step. I don't know how many numbers going to be, but what matters is the size, the increment size. So another important thing that we need to do to be mindful of here, the program stops producing number from stop minus 1 point. So when I say 2 to 30, and I don't care how many points are going to be there, it stops right before 30. The increment size would have suggested 30 includes there, but it is not like line space. Line space is a start to end, including end. List range is a start to stop minus 1. An equivalent in NumPy, which gives us an array instead of a list, is np.arrange that goes from start to stop minus 1 with the step provided. So same result, but in an array format, which is computational friendly. So this is an alternative way. So we either know the number of points we want, or we know the increment size. And let me run these. Or we could have done go from 30 to 2, decrease by 2. And stop is not going to be there, as you can see. Okay, let's dip into create arrays. So we have single arrays, we have vectors, we have matrix, and we have collection of matrices. They are assigned to different dimensions, and this is how you develop them. So for a single variable, you just say np array and then put the value that you seek to convert to an array. For a vector, you can use brackets, parentheses, brackets, v1 comma v2, and syntax is really important here. For matrix, it looks like you're developing different vectors. So you go with R1, this is a single value now, and R2, and then put them in another set of brackets showing the matrices. And like 3D goes to the third tier of brackets. And 3D essentially doesn't mean like a collection of matrices can be a collection of like two 3D, like 4D is still considered third dimension. And that's why it gets a bit of confusing, but like it is intuitive, and once you program it comes naturally to you. In order to get the dimension, the first column, we can use, given the matrix name is A, we can use A dot number of dimension, and it stands for that. So n-dim, and then to get how many rows and columns it has, a matrix, we use row, column, first number is going to be row, second is column, and a dot shape is the command. If it was a 3D, it would have been depth, row, column, and a dot shape. So let's move from the conceptual realm and let's run this and show how it works. So here I'm defining a 0D array. Just put the variable there, and as you can see, if I run this is just to show this. Here we go, we have it. Then we have the dimension of it, which is 0 dimension. Then we calculate the shape of it. Let's check the shape. It doesn't have a shape. It is just a 0 dimension. One might have said it is 1, 1. It's one column, first row, first column, and it's a single value, but it's a 0 dimension when you define an array like that. So it is not a matrix, it's just a single value array. Then we have vectors. Vectors is a bit interesting too, because what you do here is you define a 1 by 4 vector. Let's see. Yep, we have defined a 1 by 4 vector. The dimension is 1, it's just a vector. But when you go to the shape, it doesn't say 1 by 4. Vector only shows one dimension. And as you can see, like D was 0 here, there was nothing here. There's 1 here, only see one dimension. So the shape only has one of the dimensions. And it is tricky because when you want to do matrix multiplication, you get an error. And that is the reason. You think from math everything looks correct. It's a 1D, it's a vector times to a matrix, but you get an error. That's why you need to do a bit of work there that I'll get there in the next videos, but that's why I said it might be a bit different from linear algebra definitions that you have in your mind. So 1D arrays are not matrices, it's still. It turns to a matrix once you define it as a matrix. But you can use these for matrix multiplication with a bit of work that I'll explain later. So let's define first here and the second one here. Be mindful that the number of columns should be the same, otherwise it wouldn't be a matrix. So we have two rows, sorry, and 3 columns. Each of these like blue columns, they represent a complete row. And if we see the print, where is it? 12, 23, 34, first row, and the second row, and you can see we have 2 tiers of columns. So the dimension is 2 and the shape is 2 by 3 as expected. And the third one is just to have 2 matrices. Every green is an array, is a row. Then every blue is a matrix, and then different layers of, if it's like a book, every page is a matrix, and then the entire book is the 3D matrix with a collection of the matrices. As you can see here, we have one matrix here, and we have another matrix here, and we have 3 tiers of brackets. And dimension is 3, the depth is 2, the row is 2, and the column is 3. Which makes sense. And if I show them next to each other, which I wanted, because the way I printed them, when you see the 0, you don't say array, you don't see the array. It is essential to know the type is array because they are coming from NumPy. It is not a list. I just needed to distinguish that. Once we know how to generate arrays, how to generate the regular spaced arrays, once we have those tools, we can start utilizing functions. We can take natural logarithm, that is usually ln, but in Python it goes with log. And if you do want to do log in math, which is log base 10, you need to do log 10. That is very important to remember. With base 10 you go log 10. With base number nepper or natural log, you use log itself. Then you have exponential, the nepper number e1, x goes 1 and you get e 2.74, and then square root. So we have cosine, sin, tan, we have inverse cosine, inverse tan, inverse sin, absolute value, which is very common. Python sees the if you want to use tan or sine or cosine. Python accepts radian, so to convert them, if you want to put degree to radian needs to be used. Even we have hyperbolic functions defined in NumPy, and they're inverse. So this is very nice and very comprehensive. The way you use them, I'm just gonna go with simple variables like log 2, which is close to 1, and it goes with, let's do this. Log 1 is 0 as expected. Log 10.2 is this one. Then we have exp, which is 27 point something, and 27182818284. Let's make it close. It goes close to 1. And then we have absolute value, which is supposed to be positive, and then a square root of 9 is 3, and that is where we will be using round, for example. Like cosine of 60 is half. We know that, or sine of 30 is half, and because it accepts radian values, numpy, I use pi and then divided by 3, which is 60 degree, or I could have said mp dot degree to radiant instead of putting this. I should have said 60. We know these two should be half. We know 45 should be 1 for tan value, but it doesn't show that. So using round, this is just a simple computational error that happens. So using round, I can say I only need four decimal points of this. So I'm using this value inside as an input to round, and then I'm specifying I just need 4 round numbers. There is another method. Dot method can be used here again. I'm like, from NumPy I'm using sine. I'm interested in sine value of pi over 6, which is 30, and I want to only see 4 numbers after decimal, like round it for 4 numbers, and then you can see that we get the values that we expect. So these are different ways of programming it, and I would have suggested round dot round, or this one has its own usage as well, round down parentheses. And I here just use different values, and you can see here, like I'm asking the radiant value for this half degree, and it gives me the 60. But 0.1 and round would have been very useful here. So that's why we need to know round. Let's put all of these in use now. Like we have learned how to generate arrays and matrices, regularly spaced elements, how to create array, and we have seen a few commonly used functions. Now let's put them in practice, and I want to introduce how to plot to conclude this overview session, which has been long enough, I believe. And as an engineer, I do like to plot everything, and seeing over like the tools that I learned only in 45 minutes can lead me toward making plots is a it feels nice for me, so I wanna finish with this. 2D plots are very useful. We use them to even find the fault in a complex system. A simple 2D plot can help us to see through the machine and understand its behavior. To do so, we are using a PLT abbreviation that I'm shortly gonna explain, but dot plot of that library is what we use. So dot plot is a basic command, allows for various customization options. So dot plot is what we are going to use. We can define x and y coordinates, and then we have the color, G, the marker. We can have markers. The style of the marker can be specified, and these are just 2 different ways of doing it. And the style of the line that we want to draw on our coordinate, and the line width and the marker size. And then we have access to the title. We can assign a title. We can have a Y label, X label, and then we can define a legend for our plot. So these are everything that you need to know except what colors you can put there, what type of styles are acceptable, what type of markers you can utilize. I would suggest to Google plt.plot and just see and play with it and learn through implementation. And here let's see where that PLT comes from. So we use pyplot and to generate our plots from a matplot library. So we are asking pyplot from matplot library, and instead of writing matplot lib dot pyplot, we just abbreviated that as a PLT, and we are going to utilize this library to develop our plots, which is a common practice. So that's where PLT comes from. And then we have different stylings of plots that I have included. I find interesting. We can have a white grid. It would be what type of paper we want to draw our plot on, and we have different options. And the way it is done is plt.style.use, and then you put the style you want in the quotation between quotations. So I use the white grid. Let's run. Now I've imported my library. I have specified the style I want my plot to be on, and we have those. First, we can have a single figure plot. Single figure plot is just I'm gonna put one plot on that frame that I have already developed. So for sake of this example, I'm going to use sine and cosine, define an x range. So we are going to put that in use. And then I want to calculate the sine values. And here I am using a range option. And I just care about the increment size, not how many points. You could have used other like line space, np.line space, and define the number of values you want there. And as you can see, using np.arrange, I won't get 6 point something. I'm just getting 6 as the last number. However, 2 times pi is not 6. It's more than 6. So it stops at 6. And I'm getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 numbers as expected. And this is my x, this is my range. Now let's calculate y's, which are sine values of those numbers. And you can see that the function works element-wise, and it generates the values for each element on x. And we now have a range of y values associated element-wise with each x. So I have x and y. Now let's plot them. And this is what I mean by white grid. I plot it using plt.plot x, y that are already calculated, defined, and calculated. Then we have the color, the marker style, and the line style, the line width, the marker width, and there is another thing called label. Just I'm labeling this plot as line 1, and I'll define y. Then the title is sine x. The y label is y. It could have been anything. It could have been like force. It could have been vibration, anything. I'm just putting y to make everything same. The x label is x. It could have been time. It could have been movement or anything. And then the legend and the legend the Python and PLT matplot library figures out where to put the legend itself. It is smart about it. And it selects this point as the best representation of the legend, and it's sine response of x. Let's do cosine. Here is the cosine. I've calculated for the same x, and then I'm doing red and a solid line. Line width is smaller, I even didn't need the marker size because I haven't defined any marker. And let's run it. As you can see, legend smart placement, it chooses this location now. And this is the cosine. And same, I have access to different things, and I called it line 2. And the legend is cosine response. But let's say I wanted to see them together, or let's say I wanted to add another thing to this plot. There is a way of doing that too, and it is very easy. Instead of running them separately, run them next to each other, and they will be presented in the same line. I did a little bit like intermediate thing. Instead of defining z as cosine, I could have put np.cosine of x immediately here. And that's what I'm doing as a third option here. And we know that sine square plus cosine square should be 1, equal to 1, correct? And that's the purple one or magenta one. Every value is equal to 1, and because it is supposed to. So I added that one for you too, and I just put a random legend sine square plus cosine square to show you that you could have even defined a third one, and you didn't need to. This section doesn't need to be calculated separately as y and z did. You can directly put the equation you want to plot in the plot command as an argument, as a variable that it accepts. And I labeled it as live 3. And then I put first one is the leg sine, second one is cosine, and third one is x2, y2, sorry, I should have run it, and x2 plus y2. So these are, which is wrong, it is y2, z2, and y2. There we go. Now we have it. And this is using legend. There is another way of doing this. You can have legends without defining them in legend line. Let's command this. And the labels are actually kind of a legend. I could have just called legend without any argument in it, without any arguments, and it would have created legends from the labels. So it handles labels, and then it assigns the label values as legends. Or you can redefine them and it overwrites the labels as legends. And that's why you were seeing these. So I would rather to name them, and that's it. So just using few simple tools, we learned how to approach a design problem, a simple to be fair, but still feasible to attack those type of problems. And we learned how to define arrays, and through that how to define a array of elements. We have seen the functions that are mostly used in engineering, how to utilize arrays and calculate the variables for those functions, and how to plot those. I think these are great tools for someone who starts programming as engineer. These are great tools that can be utilized from the beginning. For the next session, I will talk a bit more about arrays and a concept called slicing, which is really important for us. And you will be exposed to those concepts in the next meeting, in the next tutorial, probably next month. See you soon then. Have a good one.